start.
Hello, everyone. My name is Amalrose Vayalinkal, and I am a fourth-year math specialist and psych major student at University of Toronto, St. George campus. And today I want to talk to you about virtual ring routing. So let's see. Okay. So first I'm going to be talking a bit about the setup of the problem, but just a disclaimer, I'm not a CS student or don't really have a lot of engineering background. So please bear with me as we get through setup of the scheme. So multi-hop routing algorithms describe a scheme for communication between devices. So the main goals for a multi-hop routing scheme is that we want every device can communicate with any other device, and we want to forward these messages efficiently. Right. So the main concerns when routing is memory capacity constraints of like the whole system, over-reliance on specific nodes in the network, right? Because then if those sort of communication pathways fail, then the whole system sort of messed up. Scalability, right? Like as we add more devices to communicate between, are we still able to efficiently ensure communication across all the new and old devices, right? And the length of this pathway of communication. Okay. So the premise of virtual ring routing, or VRR, is that by utilizing two different networks, the physical network and the virtual network, VRR determines routing paths between nodes independent of their location. Okay. So VRR schemes can be modeled by a pair of graphs, the physical network and the virtual network. And so here's just like a diagram where like this sort of underlying thing is the underlying physical network, whereas this ring you see here is the virtual overlay. So the physical network is an undirected graph G, where V denotes the vertices and E is the edges. And so the vertices in V are called nodes in this case, and we typically assume that there's n such nodes. And so the edges denote physical links, and a physical link means that those two devices, like an edge between node U and node V, means that device U and device V can communicate directly. Okay. And we also require that G must be connected. And I think typically in application, we would want like K connected, which means the graph remains connected even if you remove K minus or up to K minus 1 edges. And that's just because, you know, we sort of don't want it to be reliant on like one specific edge for the graph to be connected. So we want like two large connected components connected by one single edge, because then if that one edge fails, you know, the communication's all messed up. And so here's an example of a graph, and here this UV would be the physical link. Okay. And we also have the virtual network, which once we have a physical network G, we can construct this virtual network GV, where we still have the same nodes, but the set of edges now are virtual links. Okay, so virtual links are formed by chaining physical links and or pre-existing virtual links that share an endpoint. So you just sort of travel along physical links in succession. And we allow chains of length 1. So physical links can also be considered virtual links. And this just is like also helping our notation a bit later. So if UV is a virtual link, then VU is a virtual link. And that's because the physical links are bidirectional. So however you traveled from U to V, you can just sort of like trace that path back to get from V to U. Okay. And so in our earlier example, right, we had that UV was a physical link. And then a virtual link UZ might be, you would first go UV and then VZ, okay? We also require an identifier space. So to set up routing, we have an identifier space omega, which is like a well-ordered set, and it's equipped with a distance function D. So we also need a function that assigns each node to a unique ID in omega. And in virtual ring routing, we always take omega to be a subset of the natural numbers, and we assume that this function assigns ID randomly. And this is just going to help us sort of keep that like location independence that we wanted in the beginning, right? So in our previous example, we consider like U maps to 0, V maps to 3, W maps to 1, and Z maps to 4, right? So this is a possible mapping. And so then our graph, or like our physical network, changes into, you know, IDU is 0, IDV is 3, IDW is 1, and IDZ is 4. We often use V or IDV to refer to the same node, and so that's what I'll be doing henceforth. So how do we construct the ring? So the reason it's called a ring is because it's a circle, and which is like I was showing like that overlay in that earlier picture, right? There's like a overlaying circle there. And so in the beginning, that set of virtual links, EV, is empty. And so we want to start off by adding some virtual links. And then hopefully eventually we will have a virtual link between any two nodes in the network, okay? So how we start this process is by, for each node V, we set up a virtual link between V and the node with the next largest identifier, which we'll call V plus. So there's a virtual link between V and V plus if ID V plus is the minimum of all ID that are greater than ID V, okay? And so if ID V is the largest, then V plus is the node in V with the smallest ID. And this is sort of what gives us the circle, right? We just close the line that we create, I guess. No, it is always possible to create a virtual link between any two nodes in V since we require G to be connected. So, because this ID mapping is random, we don't, a priori, we don't know that V and V plus have to be close together at all in the physical network. And so we want to be able to travel anywhere along the physical network to ensure these virtual links can be made. So for example, in our earlier physical network, right? So we have that U for node U being like 0 here. The next, or like V plus would be 1. And so how we would set up that virtual link is, in this case, we're able to just do that physical link because they are, or there exists a physical link between them. For 1 to 3, we would first have to go 1 to 0 and then 0 to 3, okay? 3 to 4, again, get lucky, there's a physical link, so we can just use that as our virtual link. And then from 4 to 0, we would go 4 to 3 and then 3 to 0. Now, what if we were to add another node, right? So here we create, or we extend G by adding this node 2 here with this physical link. And so our virtual network, what happens is that 3 would be like, hey guys, I have my buddy here with me, node 2. Is he bigger or smaller than you? And this message sort of like passes along until 2 finds its place. But of course, in this case, it only has to go to 1, and 1 is like, oh, he's bigger than me, so he finds a spot there in the virtual network. And now we want to add the virtual links. So 1 to 2, well, in this case, 3 is like the proxy node for 2. So it's enough for the system to figure out how can we communicate from 1 to 3. And then 3, of course, because it's physical link, we'll just be able to forward the message on to 2. And so here we use that pre-existing link or virtual link that we created from 1 to 3, and we travel up that way, and then we go to 2. Okay? And then for 2 to 3, yeah, we can again just use that one virtual link or physical link. So what we have here is that there's physical neighbors and virtual neighbors. So in the physical network, I consider node 3, the physical neighbors of 3 are those nodes which 3 has an edge with or shares an edge with, right? So that would be 0, 4, and 2. And in the virtual network, we would have the virtual neighbors are just the next largest identifier and the next smallest identifier, so 4 and 2, okay? We also, right, when we set up these virtual links, we want to have some way the system stores these paths that we've just constructed. And that's where the routing table comes in. So the routing table at node U in V is a collection of 4 tuples, which represent coordinates from to next hop and previous hop, from V cross V cross V cross V of routing paths that go through node U. Right, so each such 4 tuple is called an entry in the routing table of U. The previous hop and the next hop nodes must be physical neighbors of U, and this is because any communication that passes through U, even if it's a virtual link, it still travels through physical links, right? Those virtual links were executed on physical links, so you can only really receive or send messages to physical neighbors. And there's one and only one entry in the routing table of U for any path that starts, ends, or passes through U. And the only one condition is there, so it's just so that if U is on a path between 1 and 2, or like from 1 to 2, we don't want there to be another entry for a path for the same path from 2 to 1, right? That's why this previous hop information is there, so that we know how to sort of travel backwards, right? And we don't have to store 2 copies of the same information, if that makes sense. And so we also have this set end U, which is a set of all nodes in the to or from coordinate in an entry on the routing table of U other than U itself. So i.e. all the nodes we know how to travel to from U. And this will be relevant later when we're actually doing the routing. So for example, like on this physical network and with this virtual network, right, we can go through how we would, or what the routing table at 3 would look like. So first we would want to add all the physical neighbors. So that's 2, 4, and 0, right? So that's just at 3, there is no next hop towards 3 because we're already at 3. So that's just a null entry. But then the previous hop was 2. And then similarly for 4 and 0, right? At 3, we're already at 3. So there is no next hop towards 3, but the previous hops are 4 and 0. And now 3 is also on the path from 4 to 0. So at 3, the next hop node towards 0 is 0 itself in this case. And so that's what this represents. And 3 receives that message from 4. 3 is also on the path from 1 to 2. So at 3, the next hop node towards 2 is 2 itself in this case. And the previous hop is 0. Okay. And we can compare this with the routing table at 2, where 2, you would add the physical neighbors of 2 first. So that's 3, which, it just send it to 3. And there's no previous hop because we start at 2. And the next thing that's the only physical neighbor. So the next thing we want to add is the virtual neighbor, which is 1. So going from 2 to 1, we're at 2. And so the next hop is going to be at 3.
Hello, there's actually a question in the chat from Shijia Yu.
I actually cannot see.
Oh, I was actually just wondering.
Yeah, go ahead.
I guess my first question is for the virtual network. So right here, you have like lined it up 0, 1, 2, 3, 4. Does that matter, like which order you put it in?
Yeah. So you're pairing it up like sequentially because you want to have the next largest identifier nearby. Yeah.
Okay. Then my next question is like at routing table at 2, for example. So the second one you put is like from 2 to 1, I guess. Should I also include like 2 to 4? Like what is it? What makes it that you don't include this? Because I assume that like they are also virtually linked.
Mm-hmm. So what we want to do is like we want to add, for sure we want the physical neighbors of any node in the routing table, and we also want the virtual neighbors for sure. These are like the minimum requirements, right? These are the minimum requirements that we have when we set up this virtual ring. So we want to have each node's physical neighbors and virtual neighbors on the routing table. And additionally, if that node is also on some path between 2 other virtual neighbors, then you would also add that so that 3 knows how to actually, facilitate this communication between 1 and 2. So in the case of 2, right? 2, we added the physical neighbor of 2, which was a 3 entry, right? And now if you look on the virtual network, the virtual neighbors of 2 are 3 and 1. And we don't want to add 3 again because actually, by coincidence in this case, 3 is also the physical neighbor of 2. So we already have an entry for 3. We know how to communicate to 3. So we don't want to add another one just because it's a virtual neighbor, right? It's already accounted for. And so then we just have to add 1. We are adding the route to 1. And now, does that make sense?
Yeah. Thank you. That's really clear. Thanks.
Yeah, and so the reason we don't add 4 is because 2 is not related to any routing to or from 4. So it's sort of independent of that. Okay, good question. Thanks for asking. And importantly, once the physical network is fixed, the routing table is fixed. So these routes are fixed, and this information on each routing table is fixed as long as we're not adding or removing any nodes from the physical network. Okay. So the next thing we want to do is talk about how we might actually route. So we just added virtual neighbors and the bare necessary virtual links to construct the ring. But we do eventually want to.
Sorry, there's another question in the chat from Anatoly. Do you want to ask your question?
Yeah. So in the routing table example on your previous slide for 2, you had an entry from like 2 to 3 and 2 to 1. Does it really make a difference as to like, could I have from 3 to 2 or 1 to 2? Or
yeah, you could. I mean, yeah. So it's sort of why I did it backwards in this example versus this example. It doesn't matter because the routing table will know how to communicate in either way. So yeah, it doesn't actually matter what order it is. And almost always when we're actually computing any like proofs or performing any computations, we always assume it's in the 2 column, the node that we are traveling to. If that makes sense. And then it's just so that we can always call it the next hop node versus the previous hop node.
Yeah, I see. Yeah, one last question. why isn't sorry, why wouldn't you just store like from two pairs for each pair of vertices? Is it just memory constraints? Like what is the like why does the routing table out2 only have 2 entries? Why not every pair of vertices?
Yeah, it is like memory constraints, because if n was like 500, we wouldn't want 500 entries. That's
Right.
not like
Yeah,
each node, right? So yeah.
Yeah, you'd have like n times n squared. Yeah.
Yeah.
Okay. Thank you.
So yeah, that was a great question actually. And so what we want to do is sort of use minimal information to construct these virtual links without having every node store a path to every other node. So the routing algorithm, the information each node has access to is its own routing table and the node to ID mapping. And recall, we can always route along the ring to our target, right? Because the circle is like connected, so we can just, worst case, travel node by node from the source to the target, right, wherever we start. And so suppose we want to send a message from node 2 to node 0. So in this case, this is called the source target pairing, where node 2 is the source and node 0 is the target, or sometimes also called like source destination pairing, if you see that somewhere. And so the question is, what should this virtual link be? Like, what should this path from 2 to 0 be, right? So here we have the ring, this is the source node, and this is the target. How might we set up this path? Well, the first thing we could try is we can consider the virtual neighbors of 2, right? So we have 3 and 1, and we can consider their distance to the target. And so we see that, okay, yeah, 1 is 1 away from 0, whereas 3 is 2 away from 0 in the shortest path. And so we can set the intermediate target, T prime, to be 1. So we're saying, okay, yeah, from 2, let's first travel to 1. Okay, and then hopefully from 1, we can get to 0. Okay? And so when we travel to 1, we travel all the way. And, we kind of didn't realize that when traveling to 1, we already went past the target. So this is not really efficient, right? Because now at 1 is going to be like, yeah, 0 is my virtual neighbor. And then the path to 0 goes up like this. So you start to like backtrack, and it would be some way, or it would be nice if we had some way of like sort of checking before we travel all the way, right? So let's try that. Again, we're at 2 and we compare the virtual neighbors and we set 1 to be the intermediate target. But instead of traveling all the way to 1, we first make 1 hop towards 1. So that's, now we're at 3. And at 3, let's again do some comparisons, right? So let's compare the virtual neighbors of 3, because that now we have, now we can also travel to these 2 things. So let's see, well, 4 is closer to 0 than 2, because 2 is 2 away. And so now we're going to set the intermediate target to be 4, okay? And when we do that route, so now we're at 2, and then we like decide to go to 4. And then from 4 now, we're like, okay, yeah, we can get to 0, let's go to 0. But then you end up back at 3. And so now if you want to compare, if you want to keep the algorithm consistent, you should really compare again at 3. But then we got stuck in some weird loop where we're just going back and forth between 4 and 3 and not really getting to 0. Maybe we could resolve this by saying, okay, at 3, we write some code in that says, oh, if you've already compared your virtual neighbors, then don't compare again, just send the message along 1 more and then do the comparison there. So maybe, okay, we do that and then 3 gets us to 0, yay. But, the issue is here, again, we are making this unnecessary backtracking, and it would be nice if we could just eliminate this deviation from this path to 0 as best as possible, I guess. And so let's try again. And this time, again, we want to first compare the virtual neighbors, and we make a 1 hop towards 3. But now, instead of just comparing the virtual neighbors, let's compare all the entries in the routing table, right? This is all the information we have access to at 3, so let's use all of it. So N3 here is 0, 1, 2, and 4, right? Those are all the nodes 3 knows how to communicate with. And conveniently for us in this case, well, that's actually the entire ring. And importantly, that is also the target. So we know that 3 knows how to communicate to 0. And so we go to the routing table entry and we say, okay, how do I go to 2? So how do I go to 0? And that next hop is 0. So we just route 2 to 3, and then 3 goes to 0. And now we could have also done the same comparison at 2, and we'll get to that in a bit, but it doesn't actually change our answer. And so let's think about what actually happened here. So at 3, we checked on the routing table at 3, And the virtual neighbors of 3 are 4 and 2, but we set the intermediate target T prime to be 0, which is actually not one of the virtual neighbors. But in contrast, at 2, end 2 end 2 only contains 3 and 1. And again, you know, by whatever comparison of virtual neighbors, we would have still set the intermediate target to be 1, even if we had compared or considered the entire routing table, because the routing table at 2 is like so small and it only contains the virtual neighbors, right? But the key difference is, right? So the key difference is that in one case, we pick the intermediate target from outside the set of virtual neighbors. So at 3, we have a greedy transition because the intermediate target that we set is not one of the virtual neighbors of 3. But in contrast, or this is in contrast to what happens at 2, where we set the intermediate target from the virtual neighbors at 2. And so that's called a non-greedy transition. Okay. Are there any questions on that? Okay, cool. So, you know, we went through a few different algorithms there. So let's just summarize the one that we settle on and the one that we like. So given a source target pair S and T, we can summarize the routing algorithm as follows. At the source node S, we pick an intermediate target T prime equals X1, let's say, from end S and forward the message to the next hop node U towards X1. Right? Because we don't necessarily have a physical link. Maybe U is X1 if they are physical neighbors, but they don't have to be, right? At U, we consider all the elements of end U. If we find, big if we find a better node, X2 in end U, then we can change the intermediate target and set T prime equals X2 and forward the next hop towards X2. So, you know, we sort of change the routing path from headed towards X1 to X2. But if no such X2 exists in end U, then we forward the message along to the next hop node towards T prime equals X1. So essentially, we just continue on the path to X1. And it's important to note that X1, right, when we set this target X1 and we forward the message along to U, X1 has to be in end U. Because by definition, U is on a path to X1. So this comparison of all the elements in end U works still, because the intermediate target at any node is already on the routing table of that node. So it's not like we're not performing the comparison well. This is a well-defined comparison so far, I guess. And once we reach an intermediate target xi, let's say, we set the next intermediate target from end xi, which again, that's also called the transition. It's just the transition is whenever you set a new intermediate target, whether that's like interrupting a route or whether you reach the destination to some intermediate target and then you pick the next one, okay? And so our hope is that, we just sort of set intermediate target after intermediate target until we eventually are able to set the intermediate target to the actual target, right? So in the previous case, that would be 0, and then we just route all the way to 0, okay? So I mentioned a better node earlier there, right? When we're looking at the routing table, we're looking for a better node. Well, what exactly is a better node? So X is a better node if the distance from X to the target is less than the distance from the intermediate target to the target, okay? Where T is the target and T is the so we want to choose the best possible X, i.e. the one that gets us closest to the target. Because sometimes there may be more than one that work, and we want to pick the one that is closest to T. And so the issue is that's not really so well defined, right? So consider this case, we're at U, right? The current node we're at is U, and the current intermediate target is V. So we're routing to V. But now suppose the routing table of U has nodes both X1 and X2 in it, like end U has X1 and X2. And they're both closer than V to the target T, but unfortunately they're equidistant to T. So how can we say what is the closest one to T? So in this case, what we would do is we would just pick the one that's closest to U, okay? And so this is like a specific choice that my research supervisor, Professor Almut Burchard, and I made. I think there's different ways to do it. Like some people just do it like randomly. If two nodes are equidistant, you would just randomly pick one. But for us, we didn't really want to travel along all the way across the ring. We just want to stay on the same side as much as possible, which is why in this case, we picked the closest one. But now we could also consider the case where they're both equidistant to U as well. So not only the target, but also it's not clear which one is closer to U. And in that case, we would just pick the smaller one because it doesn't really matter here so much the choice, okay? Or I guess, yeah, we can't really say which one's better, so we just pick this one. Okay? So here are some remarks about the intermediate targets. So each new intermediate target T prime is always closer to the target T than the previous one, right? By definition, when do we set a new intermediate target? When the distance is smaller than the current intermediate target. And this is true even if we make it all the way and we successfully reach an intermediate target, the next one will be closer because of the virtual ring, right? You have the next largest and the next smallest. So depending on where the target is relative to that target we reached, we would set from its virtual neighbors worst case. But ideally we want to hope that the routing table has some other even better node that allows us to gain a lot more distance, I guess. Okay. So at any node U, the current intermediate target is closer to the target than U or equidistant. And so this maybe is a bit hard to see why this is true immediately. But let's think about V, some node V that sends the message to U. So we know V is a physical neighbor of U, right? And say the intermediate target is T prime. And at V, we have that T prime is an end V, but also so is U because U is a physical neighbor of V. And so when V performs the comparison, if it was the case that U is actually closer to the target than T prime, then we would rewrite and we would change the intermediate target to being U because U is closer than the current intermediate target, right? So when we get to U, it's like, oh, we just reached the new intermediate target, and so now we just set a new one, right? And the only time we don't change to U is if U is equidistant, because then there's, right, the condition was that the distance was closer or distance was smaller, right? But if U and the current intermediate target are equidistant from the target, then we would not change because there's no benefit to changing. And hopefully this makes sense so far. And is there a question? Okay. And also importantly, once we set the intermediate target to being the target, there are no more new intermediate targets because of course, the target is the closest to the target. So there's never going to be a better node for us to ever set the intermediate target to. Okay, great. So there are some properties of the routing algorithm. And so proposition 1 says that virtual ring routing schemes using greedy routing exhibit no loops. So to think about this, well, if we have a loop, we must visit the same node twice, say V, right? Like if I'm going through a loop, there's this point here that I must visit twice. And so, it doesn't matter what the source or target was, maybe there's there are more edges probably here and the target's here somewhere, maybe the source is somewhere here. We don't know, but we're just looking at the portion that is the actual loop itself. Okay. Here's a small piece of the graph. And so suppose at time 1, we are at V and we perform the comparison. We look at end V and we decide, yeah, maybe we decide to keep the same intermediate target, or maybe we decide to override it. We get a new one. It doesn't matter because no matter what the intermediate target we decide at V, right, we still have that the next hop node towards that intermediate target is U1, right? So we travel this way, okay? But now at time 2, suppose somehow we end back up at V, and then at time 2, we decide to hop towards U2. So the reason this will never happen is because, well, at V, as we discussed earlier, that best node is very well defined. Either it's going to be the current intermediate target, you keep the same, or you change to a new, better one. And also, earlier we talked about the routing table is fixed as long as the physical network is fixed. So when we make this hop towards U1, that's the only route we have to that intermediate target from V, right? There's only one and only one routing table entry for any source target pair or whatever on the routing table. So we would never have the option to go to U2 because, right, there's only one intermediate target at V that's the best possible choice. And the path to that intermediate target is either going to be U1 or it's going to be U2, but it won't change from time 1 to time 2 because there's no new information on the routing table. Okay, does that make sense? Question? Let me check the chat. Okay. So while it seems that this lack of loops seems to be quite a benefit to VRR, there are other routing schemes I think that also don't exhibit loops. So let's talk a bit more specifically about the specific benefits of virtual ring routing, right? So the main one is that each node only stores local information. So less memory is used relative to the increase in size of the physical network, right? Because you're only really keeping track of your physical neighbors, your virtual neighbors, and any nodes that pass through you. That's very localized information. You can't really see the whole network. You don't know how far you are from some random node, right? You only know where you are. I mean, you also don't actually know how far you are from any node other than your physical neighbors. Those you're exactly one edge away, right? So that's a lot less information that each node has to store. And it's flexible, since adding or removing a node only affects nodes that had that node in their routing table, right? If something is changing on the other end of the graph, it doesn't affect you, it doesn't affect the routes that are in your routing table, you don't even care. You may not even know that that node was added to the system, and it doesn't affect you. You can live your life. And when you remove a node, only the nodes that sort of had to route through there, they're like, oh, now my routing table doesn't make sense because this guy's no longer here. We need to find some other way. That store on the street corner is closed, so I can't really go there anymore. Sort of like that. But it doesn't affect people on the other end of the city. Okay. So the limitations of VRR is that the routing path may not be the shortest path. So, the nodes store local information, but that means they only get to see such a small part of the graph. It's like the part that they're on and the part that they're related to, right? So they're not able to, when making routing decisions, we can't really see the entire graph and then decide, oh yeah, this is the shortest path, let's route that way, right? You can only make, short-term decisions. You can't really see or optimize long-term. And there is a way to measure, I guess, this failure to take the shortest path when routing. And that's what we define as stretch. So this is a ratio between the actual routing path, as defined by the routing algorithm, and the shortest possible path on the physical network. Okay, so we can consider this example where here's our physical network, right? Except we're going to consider it coming about by, first we have this physical network and there's a ring, and then we add this other component by, creating these two physical links between 5 and 1 and 5 and 3. And the reason we're going to do it like this, or the reason why I set up the example like this, is because, 0, the virtual neighbors of 0 are 5 and 1. And so it has a physical link to 5, so it's going to take that. And the virtual link to 1 is going to sort of take this route here. And that'll be relevant later, I guess. And importantly, this path from 2 to 1 is going to remain even in this graph here, because we could do like this, but there's no benefit, the path is still the same length. And so there's no reason to, just because these new nodes are added, there's no reason to sort of change our existing working path, okay? So, suppose again that we're routing from 2 to 0, and this is our ring now, right? So this is this current node, and this is the target. And so, we look at the routing table of 2, there's only 3 and 1, right? Because this addition here doesn't affect 2. So the routing table stays the same. And so we set the intermediate target to be 1, and we pass the message along to 3. Okay. And then at 3, well, let's make it a little bit more difficult for us. And let's assume 4 to 5, the routing path goes like that, right? Rather than doing this way. So the routing table at 3 does have both node 1 and node 5. But remember, equidistant nodes, we don't really switch if they're equidistant. So 5, even though 5 is not less than, 5 is not closer than 1. 5 is same distance, so we're not going to change the intermediate target. We're going to continue going towards 1, and so then the next hop node towards 1 is 4. So we go to 4, and then at 4, again, we have the same thing, right? We're going to compare 1 and 5, but 5 is not really better. So we continue and we reach the intermediate target 1. And at 1, of course, we're guaranteed a virtual link to 0. And so we're going to set the intermediate target to 0. And then, like I said, we're just going to go like that. Okay. And so the length of the actual routing path in this case is 5. But you and I, we're not machines. We can see that the shortest path really would have been to just go across like this. And so the length of the shortest path is 3. So in this example, we've sort of, we took the less ideal route, I guess. And that's because we store so little information, right? Imagine now like 3 not only knew its physical neighbors, but maybe if it knew the physical neighbors of its physical neighbors, right? Then we would know, oh yeah, actually routing to 5 is faster because I know 5 can definitely get in 1 hop to 0. And then we would have just taken this path, but that increases the routing table size of 3 and also every other node, right? We have to keep it consistent. So that's why this stretch thing happens, right? Stretch is not always 1. Okay, are there any questions on that? So the stretch here is 5 to 3. Okay. So now that I've sort of hopefully give you guys some idea of how virtual ring routing works and what stretch is, we can talk a bit about what I did this summer with Professor Almut Burchard, which is we want to do a careful study of stretch. So the questions are, how can we study stretch? And the main things we can do is, we can try to find some upper bound for stretch, like that would be helpful, right? And this is helpful information for people that are like trying to implement the algorithm, right? When they have to decide between which algorithm should they apply for what case, it would be nice to know that like, oh, the max stretch here is going to be this, which is like less than the max stretch here. It helps people make these kinds of decisions in actual applications of routing algorithms. We'd also find the expected average stretch across all possible routing decisions, like what is the expected aggregate stretch. We could also consider how does stretch change as n goes to infinity, right? We want to study this like a property of stretch, right? Like virtual ring routing is good because it's flexible. You can, like for Facebook, for example, if 100 people log on to, or 100 is not that large, I guess, but if many people log on to Facebook at the same time, like half of them go to bed, log off, and the other half will stay on, the ring is prepared to handle that kind of information, but we want to know like how to stretch, like how does the actual routing efficiency change under these, or how dynamic it is, I guess. What other factors might affect stretch, right? So when we say other factors, we mean like what properties of the physical network, right? So maybe there's some optimal level of connectivity that ensures like small enough routing table sizes, but also minimizes stretch, right? Because the trivial example, I guess, or uninteresting example is every node has an edge to every other node. Then the routing tables are huge, right? It's the entire network. But stretch is, of course, always 1. So because you can always, just take the physical length there. So it's sort of trying to maybe consider like what sort of balance can we reach there, right? So these are the questions that we're interested in. And the main struggles we have is setting up a good model for the physical network, right? Like I said, we want some amount of connectivity, but not too much, but not too little. We also, it would be nice if we had something familiar that we can, that both my supervisor and I are like familiar working with, and then we can apply some familiar like math concepts to, right? And also we kind of want it to have a well-defined shortest path. So this is the problem with the grid, right? So grid has a good amount of connectivity, but like a squared path, like how can I decide what the shortest path is, right? I could maybe go right and up, or I could go up and to the right. And we want it to be well-defined for, so that our computations make sense, right? We want to be able to have a well-defined numerator and denominator in the computational stretch. And the bigger issue really is computing the expected path length. And so when trying to compute the expected path length, we could think about, okay, maybe we want to just keep track of the intermediate targets. Well, the problem is, we don't know how long that path between those two intermediate targets might be, right? Maybe it's 2 nodes, maybe it's like length 2, or maybe it's length 500. Also, we don't know when we set the intermediate target, right? Maybe we reach the previous intermediate target and then we set the next one, right? Or maybe we just get one hop into that route and then we find a better node and we make that transition, right? And it gets a little bit even worse, right? Because we don't know what the physical neighbors are, right? And that could vary a lot, right? Maybe you could have 500 physical neighbors, or maybe you have just 1, right? So your routing table size differs a lot dramatically, right? And also it depends on the virtual network, but even if we were guaranteed to make a greedy transition, right? Like say, oh, I'm at U and I make some estimation for the routing table size at U, and I know for sure a greedy transition happens, right? Maybe I make this greedy transition, or I guess even this one, right? So current intermediate target is V, but we're gonna skip ahead to a non-virtual neighbor of U, and we get here. That's a greedy transition. That's great. That's pretty good. But now I could also make a greedy transition right here, or maybe even right to the target. These greedy transitions are not going to give you the same, they change the path length dramatically, right? And another issue is that, like, if I were to, say I'm at this node, what are the possible better nodes? Like when computing the probability that we reach a better node on the path to this target here, well, all of these are better nodes, except for this one, I guess, because it's equidistant, right? All of these. So, okay, that's large size, that's nice. But now if I were to greedy hop to this node here, then when I'm computing the probability, okay, what's the probability there's a better node on route to this node here? Well, in the entire network, there's only one possible better node, and that's the target itself. So I'm now computing what is the probability that the target is on these routing tables. And so that, that gets very complicated, right? So it's not really, it's we know that even if we know there's a greedy target, it's hard to say because it's like the probability is not independent at all. It's very conditional on like exact value of that, greedy, like the node that we set the new intermediate target to after the greedy transition. And so, yeah, this is the hard part, I guess. It gets a bit complicated. And so one of the things we were going to try, or one of the things we did try to sort of understand stretch a bit better, understand spreading better, is we consider the case when the physical network is also a ring. Okay, so that's what we were doing for most of the summer. And so when the physical network is also a ring, we call it a physical ring as opposed to the virtual ring. And the nice thing is that there's only two physical neighbors. And the important thing is that it's consistent across all nodes. So, when the physical network is also a ring, we have that every node has exactly two physical neighbors. And, this sort of helps with computation of routing table size because, if we know that the bare minimum that every routing table will have, it's that it's going to have the two physical neighbors and it's going to have the two virtual neighbors, right? And now either it could be the case that, well, all four are distinct, so then the routing table is like at least size 4, or maybe one of the virtual neighbors is a physical neighbor, and so then it's 3, or maybe both of the physical neighbors are the virtual neighbors, and so then the routing table minimum size is 2. And although it's not like perfect, we don't exactly know the routing table size of everything, it's still a good foundation relative to when, like I mentioned before, right? The routing table of one node should be like 500 physical neighbors versus like 1, huge difference, and makes the estimation, because there's such extremes, it makes like estimating the expected value there a bit, a bit worse, I guess. And also, if it helps in some computations, we can consider the physical ring as a permutation of the virtual ring, right? Because the virtual ring is arranged in like increasing order, but then the physical ring is sort of, the IDs are assigned randomly. And so one of the first things we did was try to compute stretch on a ring, right? Because that was our main interest. And so if the physical network is a ring of n greater than 3 nodes, then the maximum stretch for any routing path is n minus 2 over 2. And so the reason we have n greater than 3 is because, well, it's like a circle. So if it's n greater than 3, it's just a triangle, and every node is a physical neighbor of the all other nodes, and so stretch is always going to be 1. It's not so interesting, right? So for n greater than 3, consider a source target pair S and T, and suppose that on the physical ring now, right, because we can use the same measure of distance, the distance between S and T is equal to k greater than or equal to 2. And the reason we have greater than or equal to 2 is because if the distance is 1, then they're physical neighbors, and again, stretch is just going to be 1 because we would, the source node has it in the routing table, so you're always going to take the shortest path. So suppose it's greater than or equal to 2, and so here is, suppose this is our physical ring. So here's T and here's S, and then this is K. We don't know how many nodes are there, right? It's like an arbitrary N. So by proposition 1, the actual routing path either travels the minor arc, right? Or it travels the major arc, because we know there's no loops. So we're not going to ever trace back our steps. So we have to either, pick one direction to travel and then stick with it until we reach the destination. And so if we travel the minor arc, well, then stretch is 1, right? Because the length of the actual path is the length of the shortest path. We picked perfectly and everything works out, great. But if we travel the major arc, then the length of the actual path is n minus k, whereas the shortest path is k. And so stretch is n minus k over k. And this ratio is maximized when k equals 2. So that's how we get that the maximum upper bound of stretch there is n minus 2 over 2. And so now we can talk about some limitations of future directions. So while the physical ring is good, it's not really practical, right? Since it has relatively poor connectivity. If one of the on the physical ring, if one of those edges fail, then we sort of only have this one, like it's basically a line at that point. So you have to travel in one direction, not a lot of choice. It's not practical, and so while it was a good, helpful example, to sort of understand the system a bit more, it's not really helpful, I guess, in actual application of these algorithms. And also another issue is that even the shortest paths are long. So the way that we would if you were trying to find expected stretch, we would do like expected shortest, like expected length of path on the physical ring, which in the physical ring case is going to be like n/4. So that's still quite large. Like as n goes to infinity, n/4 is still massive. So that's also, again, not really representative of how we might expect stretch to be in an actual virtual ring routing situation. Okay. So where do we go from here? Well, some things we want to do in the future is we want to explore other physical network models, right? Like maybe we can somehow try to make the grid well-defined, like the shortest paths on the grid well-defined, something like this. Or maybe we want to like learn more about expander graphs, see how those work, right? So this is one of the main things we want to, find a more intricate but still workable physical network model, right? Something that we can, actually, that's a bit more interesting than the ring, I guess. We also want to try, we've also been trying to formulate the routing algorithm into Markov chain process or as sub-martingales and apply related theorems. So for those of you that are familiar with optional stopping theorem, we were thinking of maybe doing like expected hitting time of the routing path to the target, or even a node with the target in its routing table, right? And so I hope to work on these things in the coming months, as well as, explore other things related to virtual ring routing with Professor Burchard. So that's the end. Thanks for listening. And are there any questions? Should I stop screen sharing now, or? Yeah.
Thank
So
you for a very nice
I'll
talk. We will pause for 3 minutes to give the speaker a break and to give you some time to fill out a survey, which I will put in the chat
Okay.
before the
Sounds good.
questions begin. Trying to copy this. All right, there it is. Go ahead.